And when I applied this technology to people with Alzheimer's and early stage dementias, we found a certain class of molecules was very, very low in all these individuals. And I didn't know what it was at the time.
In the 1700s, scurvy was cured with vitamin C. In the early 1900s, vitamin D cured rickets and niacin cured pellagra, all crippling diseases resolved through everyday nutrients. Could there be a similar solution for Alzheimer's?
When I did the mass spec analysis, it turned out these molecules were plasmalogens. 20-30% of your entire lipid volume of your brain. 50% of the membrane of your heart is plasmalogen. But the role in cognition is even more shocking.
Alzheimer's treatment aims, in part, to rid the brain of amyloid protein plaques, first discovered by Dr. Alois Alzheimer 100 years ago. But what if that starting point is wrong?
Large neuropathology studies have shown that the location of the plaques doesn't disturb neurons around those plaques. It's not even open for question. And these pathologies are not leading to reduced cognitive functioning.
15 years of research led Dr. Dane Goodenow to discover a single molecule much lower than normal in the blood of Alzheimer's sufferers. That molecule is plasmalogen, an essential brain nutrient that gets lower as we age. Is Alzheimer's being caused by loss of plasmalogen in brain cells? And most crucially, what happens when we restore it? Welcome to Vital Signs, where we look at how to get healthier from all angles, from the biochemical and nutritional to the things we do that nourish our minds and our souls. I'm Brendan Fallon. For Alzheimer's Key to Cure Part 1 of this 4-part series, we'll learn what the Alzheimer's gene ApoE4 signals about Alzheimer's cause, and how Dr. Goodenow's invention pinpointed low plasmalogens in Alzheimer's. Dr. Goodenow, welcome back to Vital Signs.
Hi, Brendan. Happy to be back.
Great to have you back and to talk about this topic that you've produced some very promising and exciting research on, and that I know you're conducting some clinical trials into at the moment. Alzheimer's. This is something, I mean, we hear about this potential escalation, that it's going to be a massive problem with the aging population, and that's on a societal level, but this is something that impacts so many people's lives. I mean, my grandmother died with Alzheimer's. It's heartbreaking to see someone you love gradually lose their memories, and I can only imagine what the experience must be like for them to have those things slip away. Obvious question is there anything that can be done about this? Because generally it seems that the medication isn't doing a lot, and is there hope for really treating someone who has this condition?
Well, absolutely. So the short answer to can you recover from Alzheimer's disease, and the answer to that is an absolute, unfiltered yes. So that is doable. And it's one of those stories. Alzheimer's is, it's a scary disease. It's now considered one of the top most feared diseases in the world. And cancer used to be that most feared disease for most people for so many years. And now Alzheimer's is basically right up there with cancer. Even though 6 times more people will die of cancer and more people will die of heart disease than will die of Alzheimer's. So the fear of Alzheimer's gives you an understanding of why this is such a devastating disease. And it really comes down to, the concept of if you die of cancer, you still die as yourself with cancer. Like you actually die with cancer. When you die of Alzheimer's, you don't even die as yourself because your brain and your mind and who you are has gone.
When you think about Alzheimer's, people understand it to be the cognitive decline, people's memory, people's mental functioning declines. So what do people actually die of if they're dying with dementia or with Alzheimer's?
That's a good one. Most of them die of actually lung-related infection issues because they get institutionalized. So the typical the process is the following, right? Your loved one gets diagnosed with Alzheimer's disease. They can typically stay in their home with a caregiver for a couple of years, maybe 2 years, maybe 3 years on average. And that'll be very broad, depending on the quality of the care they can get at home. And then they move into a long-term care facility because at some point in time, the family and the caregiver, their health deteriorates. They can't take care of that person and they need more sophisticated, skilled nursing care. But yeah, so pulmonary failure, heart failure, are the things that they typically die of some other related core physiological breakdown. And this is the other part people forget. There is actually only one type of death in this world. Okay, like you don't actually die of a heart attack. You don't actually die of pneumonia. You die when your brain loses oxygen. Okay, there's only one type of death, is brain death. And the entire part of your body is basically designed to keep your brain alive.
Dr. Goodenow, How did you come to be researching this? Where did your research with Alzheimer's begin, and what has been the major discovery there?
Yeah, that's an interesting story because my background is in synthetic organic chemistry. My PhD is in psychiatric medicine, looking at the biochemical mechanisms of disease. This is what I was trained in, looking at understanding how the brain works. And so I came into the Alzheimer's understanding biochemical mechanisms, understanding the prodrome, what occurs in an individual before they get Alzheimer's. Because Alzheimer's is not something you get. You lose cognition. Okay. You have a healthy functioning person in their 30s, 40s, 50s, 60s that are cognitively normal, fully interactive with their environment, and they lose that. Okay, so Alzheimer's is not something that comes into you and, like a Pac-Man and starts eating at your brain. Like that's not what's happening. You actually lose function. So slow thinking, inability to pull up memory, inability to have executive functioning, these are actually functional activities of our body. Back in the 90s, when I started getting into this research in great detail, it was in the height of the genomics revolution. People were sequencing the human genome, they're sequencing plant genomes and animal genomes, and they were trying to find the genetic associations with everything, right?
What is a genome in just a snapshot?
So the genome is what you're born with. So the genome is your DNA. Every single cell of your body has exactly the same DNA. And that DNA gets expressed in different ways. Like your heart cell will express this DNA slightly different than a lung cell, slightly different than a brain cell, for example. With the vaccines, people talk about the messenger RNA stuff. That's how your genome expresses itself. And this messenger RNA then is used to create the proteins, the physical structure, the receptors, the ion channels, your muscles, all that protein in your body is built from your DNA. So every single protein in your body can actually be linked back to a specific gene, sequence-wise. But really, what's interesting about Alzheimer's is there is a genotype called the apolipoprotein E genotype, E2, E3, E4. And the E4 genotype has a higher probability of dementia. And this was only discovered, I think, in the 80s. ApoE is a cholesterol transport protein. It's a type of HDL molecule that transports cholesterol in our blood. But what makes ApoE so unique is that it is fundamentally the exclusive cholesterol transport protein in the brain. So the brain makes all of its own cholesterol. So the cholesterol in your blood never ever reaches your brain. Okay. In fact, your brain makes its own cholesterol and sends it into your blood supply. So when happens in your periphery, you have what I would call an interstate highway system of transport. Your veins, your arteries, they're shipping blood and cholesterol and nutrients all very, very long distances. So they have these super highways, okay? But your brain is not built that way. Your brain is like Chinatown. It's like a little bunch of little side streets. So you don't have trains and big semi trucks transporting things. Things are transported on smaller things that can get in and out of all the little vesicles of the brain.
It's like a microcosm of a larger city.
Correct. And so it uses a bunch of small trucks, if you will. And that small truck is ApoE. And so in Alzheimer's disease, what they found, so even though we knew about the ApoE genotype way back in, I think, the 60s and 70s, because it's so people that have certain rare blood diseases, they've been knowing about this for a long time. But somehow, I think it was Dr. Rose's and those group out of Duke at the time, they discovered randomly, they were doing this genetic association study, and they realized that people that had this E4 genotype had a higher, twice the rate of Alzheimer's was in this group of people. So this was a big, big discovery in terms of understanding Alzheimer's. And it really led to the cholesterol hypothesis in Alzheimer's of the cholesterol membrane structure of the brain, because ApoE is a cholesterol transport protein.
This was in the 70s, you said?
Yeah, well, we've known about ApoE for peripheral blood cholesterol disorders. People that are born with, say, a LDL deficiency, the other protein for LDL is called apolipoprotein B. People that can be born without any of that. And those individuals, the ApoE genotype takes over and actually builds up enough so they survive. So the body has these compensation mechanisms. But it was in the 80s that they found that there was an association between people that had the E4 genotype and Alzheimer's, which opened up probably the largest bolus investment of money trying to understand the ApoE4 genotype and its role in Alzheimer's in the history of man. Like there was just an enormous amount of research put into that. So it clearly tells us that cholesterol regulation in the brain is related to Alzheimer's, and it absolutely is true. And this is where, you know, we're jumping ahead to the story, but we'll talk about plasmalogens in a little bit. What the ApoE4 genotype does, or the ApoE protein does, it's responsible for sharing cholesterol from one cell to another in the brain. And in order for the cholesterol to be shared, it goes onto this ApoE particle and gets shared. Then, but the other side of this three-legged race, if you will, is plasmalogens in the brain. So the cholesterol export is dependent upon plasmalogen levels in the brain. So when you have low levels of plasmalogens, the cells can't export their cholesterol. So you get a double whammy. So I published this pretty extensively, that people that have high levels of plasmalogens in their blood, it neutralizes their genetic risk for Alzheimer's disease. So if you have high levels of plasmalogens and you are an E4 carrier, you do not have an increased risk for Alzheimer's. So it neutralizes that risk.
You can find links to Dr. Goodenough's Alzheimer's relevant studies in the description below. Coming up in Alzheimer's Key to Cure Part 2, I speak to the stepson and husband of a lady diagnosed with early onset Alzheimer's. For the first time in 10 years, they are experiencing hope for her condition after starting plasmalogen treatment.
Her inability to walk, stopped communicating, stopped smiling. She would just sit and stare at a wall and wouldn't recognize you when you walked in the room.
Good job, Carolyn. Carolyn, you're on video, hon.
As a matter of fact, Carolyn came out this morning pushing a walker, which she has never done before. Like, she hasn't done that for how many years now? So I was, again, at the stage where I was almost crying, because it was just awesome to see that.
To get notice of that and other new Vital Signs videos, follow me at Vital Signs Brendan on Instagram, and that's SEE Vital Signs on X.
So yeah, so this is where the story, so we jumped into this damn genetic side of things. So that's where this all started for me, was back when this genomics revolution was occurring. We had this very advanced genomics technology to measure all the genes in the human body or animal bodies, and we could measure the function of those genes. Like we could change them with functional genomics, but we had no way of actually measuring what was ultimately happening. We didn't have a complementary technology that could measure thousands and thousands of molecules. So I invented a technology called non-targeted metabolic profiling. It uses a very big ion cyclotron mass spectrometer and allows us to measure thousands and thousands of molecules simultaneously.
You said before that this is something like it kind of works like an MRI machine, right?
Yeah, it's a 7 Tesla or a 9.4 Tesla. A normal MRI, like your advanced MRIs, are 3 Tesla magnets. They're superconducting magnets. They're housed in liquid helium, and they give the ability to make extreme high resolution of small molecules. And by doing that, if you can measure every unique combination of atoms actually has a unique mass. And if you can measure the mass accurately enough and you can resolve them from one another, then you can, without having any a priori knowledge, without actually knowing what the molecule is in advance, we can measure it, find the accurate mass, convert the accurate mass to a molecular formula, and then derive the molecule after the fact. So this changed everything. So now I don't have to know, I don't actually go looking for something. So it changed it from saying, I wonder, is there association between homocysteine and Alzheimer's disease? Is there association between, phosphatidylcholine and Alzheimer's disease? So prior to my invention, everything had to be hypothesis driven, because you had to develop a method for one molecule or a group of molecules at a time, and then try to say, okay, I'm going to test this molecule. But you had to know what you want to look for before you did your study. So you had to actually, in advance, have some understanding of what you're going to measure. This changed all that. It says, you know what? We're not even going to think about it. We're going to do studies. We're going to measure people with that are normal, people with cognitive impairment, different levels of cognitive impairment, or with cancer, or with autism, or with bipolar disease. Doesn't matter the disease, right? We're going to measure these diseases, and we're going to look at the biochemistry in a completely non-targeted way, and we're going to see what comes out of that. And when I applied this technology to people with cognitive impairment, Alzheimer's and early stage dementias, we found a certain class of molecules was reproducibly very, very low in all these individuals. And I didn't know what it was at the time. And when I did the mass spec analysis, it turned out these molecules were plasmalogens. Right. And I go, I never heard of a plasmalogen before this. Okay, completely out of the blue, was not looking for it. And so, of course, I get on there and I start Googling it and I start looking for what the heck is a plasmalogen. And it turns out we've known about these things since the 20s or 30s. We know genetic diseases that have plasmalogen deficiencies are terrible. Like they have early mortality. Children are dwarfed. They have neuromuscular disorders. We did an episode on children with that rare disease, rhizomelic chondrodysplasia punctata. So this plasmalogen deficiency led me to understand what is going on here. Is this just a bystander for an accident? Is this just a symptom of the disease, or is it somehow related to the underlying mechanism of Alzheimer's?
What is a plasmalogen in a nutshell?
Right. Well, yeah, so that's exactly what I had to figure out, right? So plasmalogen is a phospholipid. It's part of your biological membranes of the body. And all of your cells are made of membranes. The membranes comprise the three-dimensional structure. They're what control what goes in and out of your cells, how your cells signal, neurotransmitter release, the heart function, lung function, kidney function. All those things are highly, highly dependent upon appropriate membrane structure. And so the plasmalogen is a core component of all those membranes. But the plasmalogen molecule, this is where the story gets very, very interesting, is we do not get that in our diet at all. The human body makes 100% of your human need for plasmalogens. And the human need for plasmalogens is not small. We're talking 20-30% of your entire lipid volume of your brain. 50% of the membrane of your heart is plasmalogen. And people will die of all different types of causes: cancer, cardiovascular disease, pulmonary disease, because plasmalogens are core to those things. But the role in cognition is even more, I would say, shocking, because it deals with the core operating construct of the human brain.
Coming up in Alzheimer's Key to Cure Part 2, we probe how the Alzheimer's brain could be restored through plasmalogens.
Vesicular transport process is entirely dependent on plasmalogen levels in the synapse. How your cells signal, neurotransmitter release, the heart function, lung function, kidney function, all those things are highly, highly dependent upon appropriate membrane structure. And this is where the plasmalogen story gets so exciting and scary and hopeful.
Check the description below to see if that video's already been published. If not, the link will appear there soon.
So when I started looking into Alzheimer's and the Alzheimer's pathologies and the progression of the disease, looking at from first principles what's actually going on in the brain versus what people are kind of flippantly telling you is going on, those two become a very different reality. And so that's kind of where the story should really start, is the difference. What is Alzheimer's?
What is Alzheimer's?
Okay. So Alzheimer's is a medical doctor called Alois Alzheimer's back in the early century, I think 1906, in that range. He was treating a woman who had early dementia and eventually did the autopsy of her brain.
Just a second, Dr. Gooden, I think we need to have a little definition of dementia there just to put it in context.
So dementia is basically loss of mental function. It's exactly what the word says, dementia, like you have loss of mental function. And typically the earliest signs of dementia is cognitive impairment. Those are the first things we lose. Our memory, you lose your keys, you can't find your words, all those things and you can't remember short-term events. Okay, you can't remember what you had for breakfast. You can remember what you had for your prom, but you can't remember what you had for breakfast. Yeah, so what happened with Dr. Alzheimer's is that he had a patient that had dementia. So the first knowledgeable thing that he knew was that this was an early dementia patient. This was a young woman who should not have dementia. Okay, so here was an abnormal functioning person, and he was trying to figure out what was wrong with this person. Right. So first thing, he already knew something was wrong. So he wasn't guessing. The person had dementia. Then he was saying, okay, can I find anything that could potentially be the cause of what I'm clinically observing? And then he goes into the brain and he finds these pathologies. She had these amyloid plaques. I didn't call it amyloid back then. It was called agrophilic plaque formation in the brain that was happening between the neurons. And they had these tangles, these neurofibrillary tangles. So he says, these pathologies are potentially linked to this clinical observation that I'm seeing. And so that's why Alzheimer's disease was considered pre-senile dementia. So people that were getting dementia very, very early in life, and that was a pathological diagnosis or causation. And because most people felt that senility, okay, was caused really by hardening of the arteries. It's more of a cardiovascular type vascular dementia, which we still have today. That was the general belief for most of the century.
And it's almost expected that this is going to happen as people get older. Their cognition is going to decline.
Exactly. But then what happened was in the 60s and 70s, they started doing autopsies on elderly people with dementia, people that got dementia later in life. And they were seeing the same pathologies that Dr. Alzheimer was seeing in people later. So then they created a category of dementia called senile dementia of the Alzheimer's type. So Alzheimer's is a type or a classification of a dementia. So they called it senile dementia of the Alzheimer's type. Clearly, the Alzheimer's disease, which is the pathology, is not the actual cause. Because if Alzheimer's disease was the cause of dementia, then we wouldn't have Lewy body dementia. We wouldn't have frontal temporal lobe dementia. We wouldn't have vascular dementia. There would only be Alzheimer's dementia. And that's not what we see.
And Dr. Gooden, now, so dementia, Alzheimer's, is dementia that is marked by the presence of these amyloid plaques and Dow particles specifically. That's what dementia Alzheimer's is.
Right, but Alzheimer's disease is a purely pathological thing. Okay, if I take your brain and you can be completely cognitively normal, a fully functioning human being, and you go for an autopsy and you can have Alzheimer's disease. Okay, just because you have Alzheimer's disease does not mean you have dementia. And in fact, 30, 40, 50% of people who are cognitively normal when they die, if the neuropathologist looks at their brain and doesn't know your cognitive status, the neuropathologist will diagnose you with Alzheimer's disease.
Wow.
Okay, and so there's a very, very large disconnect. So
we obviously don't have that many people experiencing cognitive decline, so it's obviously points to other reasons why people are experiencing this.
Correct. Now, don't get me wrong. You're not supposed to have amyloid plaque in your brain. You're not supposed to have neurofibular tangles in your brain. That's not a good thing. Okay, so but the point is that there's a different mechanism associated with these pathologies. And these pathologies are not leading to reduced cognitive functioning. Okay, there may be an association, but they're not causal. And we've known this very unambiguously since the 90s. Large neuropathology studies have shown that the location of the plaques doesn't disturb the actual neurological functioning of the neurons around those plaques. It's unambiguous. It's not even open for question.
That was Alzheimer's Key to Cure, Part 1. We learned how cholesterol transport may be more key to understanding Alzheimer's than amyloid plaques in the brain. You'll find the link to Alzheimer's Key to Cure Part 2 in the description below once published. It's been great to be with you. I'm Brendan Fallon, and this is Vital Signs.